Hey fellow nerds, today we are going to learn some biasing techniques that are used in common emitter configuration. We will start by understanding the common emitter configuration, then move on to biasing, operating point or Q point, DC load line analysis, fixed bias, voltage divider bias, biasing with emitter degeneration and self bias. First, let's have a recap on how we decided to build an amplifier. This was our idea. We wanted a current source that was dependent on a voltage over here. I is proportional to V1. This idea was realized by using a BJT in the circuit like this. The collector current IC depends on whatever is the voltage we give between the base and the emitter. Right now in this circuit, that voltage is the input voltage. So the actual relationship between the collector current and the input voltage will be like this. IC is Is e raised to V in by Vt. One problem we have here is IC and input voltage are exponentially related in this equation. But when we made the idea of an amplifier, we said the current should be proportional to the input voltage. We did an approximation on this. We saw that if the input signal is small enough, the equation can be written like this. IC is IC naught plus GMV input. This is a linear equation. So IC here is directly proportional to the input voltage. So in the original equation, IC and the input voltage had an exponential relation, but now they have a linear relation, which was exactly what we wanted. So for small signals, we can say the current that we get is actually proportional to the voltage that we give. Let us draw this circuit in a better way now. This is the exact same circuit. Now, one important thing is for a transistor to work as a voltage controlled current source, its base emitter junction should be forward biased and collector emitter junction should be reverse biased. To reverse bias the collector emitter junction, we put a cell over here in this direction. We have applied the input voltage between the base and the emitter. Positive potential at the base, negative potential at the emitter. So ideally the input voltage will be forward biasing the base emitter junction. But there is a problem. We have assumed that our signal is small. Its amplitude will not be enough to forward bias the base emitter junction. So we have to add an extra cell over here in this junction that will keep the base emitter junction in forward bias. We call that method biasing. Let us again modify this circuit in a different way. Let us check out the differences I have made. The first thing is over here you can see the output is taken between the collector and the emitter. Here also output is taken between the collector and emitter. I have just shown it in a different way. You can see that the output is taken between the collector and the emitter. Instead of showing the load resistor over here, I have shown it over here. Connections are still the same. Its upper end was connected to the collector. It is still connected to the collector. Lower end was connected to the positive terminal of VCC. It is still connected to the positive terminal of the VCC. One more difference is instead of calling this the load resistor RL, I have called it RC or the collector resistor because it is connected to the collector. So the input is given between the base and emitter. Output is taken between the collector and emitter. Emitter is common. Because of that, this is called common emitter configuration of a BJT amplifier. Or simply, you can say this is a common emitter amplifier. Now, something else we can do here is this. We can consider the potential of the lowermost point to be 0 and define the potential of every other point with respect to that. This technique was used to solve some problem in the last video. Basically, what we are doing is taking the lowermost point as the ground. Using this idea, we can represent the same circuit in a much simpler way like this. You can see that all the connections are the same. Negative terminal of V0 goes to the ground. Here also it is going to the ground. Emitter is connected to the ground. Here also emitter is at the ground. VCC is a cell that is connected between this point and the ground. Over here, instead of that, I have shown it as just a supply that is given at the collector. But you should know that basically it is just a voltage source, just like the cell that we have over here. So from now, we are going to be using the simplified diagram for our analysis. Let us move on to biasing. We know a bipolar junction transistor operates as an amplifier if it is biased in the active region, which means in the absence of signals, the base emitter junction and the base collector junction should be forward and reverse biased respectively. To forward bias the base emitter junction, I have connected VBE over here. To reverse bias the collector emitter junction, I have also given VCC. By giving a proper value of VBE, I will get a proper value of IC over here. So we can say that biasing provides proper voltage and current so that the transistor can amplify. Assume that I am giving a VBE value of 750 millivolt. Upon calculating, I can see the collector current is going to be around 1.7 milliampere. Let us show that on the IC versus VBE graph over here. VBE is 750 millivolt, and because of that I got a collector current that is equal to 1.7 milliampere. So technically we can say that the BJT is operating at this point on the graph. We call it the operating point or the Q point. It is defined as the bias values that we have chosen for VBE and IC. For example, here we have taken VBE to be 750 millivolt and IC to be 1.7 milliampere. When we say Q point, the letter Q stands for quiescent. Quiescent means inactive or at rest. The operating point is called quiescent point because we haven't applied the input yet. We are simply doing the biasing. So we can actually consider the amplifier to be inactive or at rest because it is not amplifying any signal input right now. We are just preparing it for amplification by biasing. Amplification properties like GM, R-pi and R0 will depend on the quiescent collector current. Now, directly connecting a cell over here between the base and emitter is one way of biasing it. Right now, you can see we are giving two sources. We have VCC over here, VBE over here. Why do we need two sources? Do you think instead of connecting VBE between the base and emitter, we can directly connect VCC to the base so that the base will be at a higher potential than the emitter? Like this. The base right now has a potential that is equal to VCC and emitter is grounded, so it has 0. With respect to the emitter, base has a potential VCC which is positive. That means the base emitter junction is forward biased. Sounds good, but let us see what happens when we apply an input. I have applied the input between the base and the ground. Since the emitter is also grounded, you could say the input is between the base and emitter. Base is directly connected to the VCC. Emitter is at the ground. So the potential difference between the base and the emitter is VCC. Now I can model this circuit in this way. Instead of directly connecting the base to VCC, I have shown the same effect by adding a cell over here between the base and the ground, and its potential is VCC. The cell of potential VCC is connected between the base and the ground, but emitter is also grounded. So basically we have a potential of VCC between the base and emitter, just like what we have over here. So let us model this circuit this way for analysis. Let us also show that we are taking the output at the collector over here since this is a common emitter configuration. Now, do you think this circuit is going to work? Will it give me an output that is an amplified version of the input? To understand that, first let us write the expression for output voltage. We are giving VCC here. According to Ohm's law, ICRC will be dropped across the collector resistor. Whatever is left will be dropped over here. So output voltage is going to be VCC minus ICRC. Here VCC is a fixed value. RC is also a fixed value. So V output depends on our collector current. And collector current depends on whatever is the potential you get between the base and the emitter. Here we have given the input voltage between the base and emitter. True. But we also have VCC between the base and emitter. Technically, the base and emitter is shorted through the cell whose potential is VCC, which means it doesn't matter what your input voltage is, potential across the base and emitter is always going to be VCC. If the base emitter voltage is constantly going to be VCC, IC is also going to be a constant value. V input will not be able to influence IC. That means VCC is a constant, RC is a constant. Not only that, IC is also a constant, which technically means V output is also going to be just a constant. It is not going to be an amplified version of whatever is the signal input you are giving. Instead, you will get a constant value. Let us write this down. Input signal is shorted to VCC. So the changes in the input will not affect VBE. VBE is going to be constantly at VCC, which means V output is going to be a constant value. So obviously, this is not going to work. So let us try this. Instead of taking positive potential from the VCC directly, I will take it through a resistor like this. Since we are connecting the resistor to the base, we will call it RB for the base resistor. By adding a resistor, we can make sure that the base emitter junction is not being shorted. Biasing a BJT this way is called fixed bias. Let us do the analysis and see how this works. Before we start, I have one question to ask. How many loops do you see in this circuit? 1, 2, 3, 4. Okay, very obviously we have this one loop. So whoever thought 1, congratulations, you couldn't be more wrong. Remember, our supply voltage VCC can actually be modeled as a cell like this, which means we have a loop that looks like this through the collector and emitter. So we call this the collector emitter loop. So we have two loops, right? Wrong again. VCC can be modeled as a cell of potential VCC like this between the topmost point and the ground. That means we have one more loop like this through the base and emitter. So we can call this the base emitter loop. So basically there are three loops. To make the loops more visible, let me draw the circuit in a different way like this. Let's apply KVL in the base emitter loop. I'll start from this point and go clockwise. I can see VCC from negative to positive. As I go forward, I can see RB. Current through RB is the base current in this direction. So base current through RB is flowing in this direction, which means positive potential is here, negative potential is here. Its direction is opposite to VCC, so I will write minus IB RB. As I go further, I can see the base emitter junction. Positive here, negative here. So I will have to write minus VBE. These are all the potential drops we have in the loop. So this should be equal to 0. From this, I can write an expression for the base current IB. It is VCC minus VBE divided by RB. We want an expression for collector current, but we know collector current is beta times IB. So IC is beta times VCC minus VBE by RB. Let us now apply KVL in the collector emitter loop. I'll start from this point and go counterclockwise. As I go, I can see VCC from negative to positive. As I go on, I can see there is RC over here. Current flowing through RC is the collector current and it is flowing in this direction, which means RC should have positive potential here and negative potential here. It is opposite to the direction of VCC, so I will write minus ICRC. As I further go on, I can see the collector and emitter. Whatever is the potential across the collector and emitter, I will call it VCE. It will also have positive here and negative here, so I will write minus VCE. These are all the potential drops in the loop, so the sum should be equal to 0. From this, I can write an expression for VCE. It is VCC minus ICRC. But IC is beta times VCC minus VBE by RB. So we can write VCE is VCC minus beta times VCC minus VBE by RB multiplied by RC. Now, we need the transistor to be in the active region so that it can amplify our input signal. For that, VCE should always be greater than VBE. Otherwise, the transistor will go into saturation. So, to avoid saturation, we have to make sure VCE is greater than VBE, or VCC minus beta VCC minus VBE by RB multiplied by RC is greater than VBE. We got VCE is VCC minus ICRC. I want to plot a graph of IC versus VCE. For that, I will write this equation this way. IC is minus VCE by RC plus VCC by RC. I can see this is a linear equation. Let us compare it with the equation of a straight line. I'll take IC on the y-axis and VCE on the x-axis. That means slope of the graph is going to be minus 1 by RC. I will get a negative slope. Y-intercept is going to be VCC by RC. If I plot the graph, this is how it will look like. When VCE becomes 0 in this equation, IC will be VCC by RC. That is why over here I have marked VCC by RC. Also, when IC becomes 0, here VCE will become equal to VCC. So over here I have marked VCC. Again, in this equation, the only variables are IC and VCE. RC is the resistor that we give over here. It is a constant. VCE is our supply voltage. It is also a constant. So basically what this graph means is this. If your VCE is this much, the IC that you get will be this much. If your VCE is this much, the IC that you get will be this much. If your VCE is equal to VCC, IC will be 0. If you remember, we had plotted another graph of IC versus VCE. It looked like this. We saw that for different values of base emitter voltage, the collector current saturated to different values. By overlapping the two graphs, this is what we have to understand. For example, assume you gave VBE3 for your base emitter junction. Then the collector current you get is going to be this much. Now the question is, how much should be your VCE for this to happen? Obviously, it has to be this much. Because according to the straight line graph, if this is your collector current, then VCE has to be this much. Can you guess in this example where will be our Q point? We chose VBE3 that gave us this much current. For this much current, we need this much VCE. That means our Q point is over here. So the straight line graph that we got represents the relationship between the DC voltage VCE and the DC current IC in the circuit, and it is determined by the load resistor RC. Because of these reasons, we call it the DC load line. The DC load line helps us to analyze the operating point or the Q point of the transistor. Let's do something. Assume that I chose VBE2. That gave me this much of collector current. But for this much of collector current, I need to have this much of VCE, which means my Q point is over here. Now, what would happen if instead of VBE2, I chose VBE1? Then I would get this much collector current, which means I would need this much VCE. My Q point would be over here. The same way, if I chose VBE3, the Q point is going to be over here. For VBE4, it is going to be here. So for different base emitter voltages, the Q point is going to move up and down on the DC load line. Let's go back and try something else. Let us call this VCC VCC1. That means VCC by RC will become VCC1 by RC. I want to plot the DC load line for different values of VCC. For example, assume I am taking VCC2 and it is over here. That means here also I will get VCC2 by RC, which is obviously going to be lesser than VCC1 by RC because VCC2 is less than VCC1. The graph will look like this. I am only changing VCC and not VBE. My VBE is still at VBE2. My question is, what will happen to the Q point? VBE2 is supposed to give me this much collector current. But according to the new load line, this much collector current requires this much VCE. So my Q point will be over here. For another value of VCC, we might get something like this. In this case, the Q point is going to be over here. So we can say when VCC is changed, keeping everything else the same, Q point is going to move horizontally. Let's again go back and try something else. This time I want to change my load resistor RC. First I will call this one RC1. Now if I take a different RC, RC2, which is greater than RC1, VCC by RC2 is going to be lesser than VCC by RC1, so I will get a point over here. But I haven't changed VCC, so this point is still going to be here. The graph will look like this. VBE is still VBE2, that means I should get this much collector current. For this much collector current, according to the new load line, I should have this much VCE, which means my Q point is now over here. Let me take one more example with R3, which is even greater than R2. The graph will look like this. Here the Q point is going to be over here. Let's have a look at the three variations together. If you change the base emitter voltage, this is how Q point shifts. If you change VCC, this is how it shifts. If you change RC, this is how it is going to shift. Let us see an example. We have to solve a problem. Given the load line and the defined Q point, determine the required values of VCC, RC and RB for a fixed bias configuration. First, let us take a transistor under fixed bias configuration. Let us analyze the DC load line. We know when IC becomes 0, VCE will be equal to VCC. That means this point over here should show VCC. VCC should be 20 volt. We also know when VCE becomes 0, IC is VCC by RC. In the graph, what we have over here is 10. So 10 has to be equal to VCC by RC. We already know VCC is 20 volt. So from here, we can find the value of RC. RC is 20 divided by 10 times 10 raised to minus 3. That is 2 kilo ohm. We also have to find out the base current IB. If you take a look at RB in the circuit, you can see it has VCC on one side and on the other side it has VBE. So the current that flows through it will be VCC minus VBE divided by RB. And that will be our base current IB. From this equation we can write RB is VCC minus VBE divided by IB, or 20 minus 0.7 divided by 25 microampere. That means RB is 772 kilo ohm. Now, there is an important thing that we have to note regarding fixed bias. We saw IB is VCC minus VBE by RB, and that gave us collector current IC is beta times VCC minus VBE by RB. Or basically, the collector current IC depends on beta. But the problem is, beta is significantly influenced by temperature. When we bias a transistor, we want it to be stable. Once we have chosen a VBE and an IC, once we have chosen our Q point, we want it to stay there. But right now, you can see IC depends on beta, beta depends on temperature. That means our IC is not going to be constant, which means our Q point is not going to be stable. To show you how bad this is, let me take an example. I have taken the base current to be 25 microampere, VCC is 6.5 volt, RC is 2 kilo ohm, and beta is 100. I already have the values of IB and beta, so I can find IC. It is beta IB, which is 2.5 milliampere. We know VCE is VCC minus ICRC. Let us substitute all the values. That gives us VCE is 1.5 volt. We know the condition for a transistor to stay in active region. VCE should be greater than VBE. Here VCE is 1.5 volt, which is obviously greater than VBE. VBE for a silicon based transistor can be considered to be 0.7 volt. So we are good. Now, assume that due to some temperature change, beta became 120 instead of 100. If beta becomes 120, the new collector current is going to be 120 times base current. That will become 3 milliampere. Originally, it was supposed to be 2.5 milliampere. It is 0.5 milliampere more. Percentage wise, there is a 20% increase, which is really high. Let us see what happens to VCE in that case. The new VCE will be VCC minus the new collector current multiplied by RC. If we give the values, we get 0.5 volt, which is obviously less than VBE, which means our transistor is going to saturation. It is not going to work as an amplifier anymore. So somehow we have to make sure our collector current does not depend on beta that much. For that, let us try a new technique for biasing. Instead of taking VCC through one resistor, I am going to take it using a voltage divider circuit. VCC will be divided between R1 and R2, and whatever R2 gets is going to be supplied between the base and emitter. Let us see how this works. We have to start the analysis by making an assumption that the base current is very small, it is negligible. I'll explain the reason. We have VCC over here, so obviously some current is going to flow in this direction. At this junction, some of the current has to flow in this direction, that is the base current. The rest will be going to R2. If some of the current coming here is going into the base as base current, that is going to affect our voltage divider. We assume that the base current is so less that whatever is the current flowing through R1 is going to be almost exactly what is going through R2. In that case, we can take this loop. VCC is actually a cell connected to the ground. Here also we have the ground. We have R2. We have R1. So the current flowing through here is going to be VCC divided by R1 plus R2. Because basically R1 and R2 are in series if we ignore whatever is happening here. So to ignore whatever is happening here, the current flowing through this has to be negligible. Let us note it down. Base current is so small that it is negligible, so we can ignore whatever is happening at this junction. Let's mark the current flowing through R1 as I. I flows through R1 like this. And since the base current is negligible, almost all of the current will flow through R2. So the current through R2 is also going to be I. You can see that I have marked this point as X. What will be the potential at X? We have applied VCC over here. It will be divided between R1 and R2. And whatever R2 gets is going to be Vx. Vx will be VCC divided between R1 and R2 and whatever R2 gets out of it. Or we can write R2 by R1 plus R2 multiplied by VCC. Now, one thing you can see is this end of R2 is connected to the base of the transistor. The other end through the ground is being connected to the emitter. So the base emitter voltage is basically whatever is the voltage across R2. But what is the voltage across R2? It is Vx. So here VBE is Vx. Now we know the collector current IC is given by Is e raised to VBE by VT. Instead of VBE here, we can write Vx. So collector current depends on Vx. What does Vx depend on? It depends on the values of the resistors and the supply voltage VCC. Does it depend on beta? No. So does collector current depend on beta anymore? No. Collector current becomes independent of beta. Now, how will the DC load line look like? Let us take the collector emitter loop. VCC is basically a cell that is connected to the ground like this. So we have this loop. If we apply KVL, we get VCC minus the potential drop across RC, which is ICRC, is going to be the rest of the potential, which is the potential between the collector and emitter, VCE. Or in simple words, we can say VCC is supplied, ICRC will be dropped across RC, the rest will be between the collector emitter. The rest will be between the collector and emitter. So VCE is going to be VCC minus ICRC, the same as the fixed bias configuration. So for the DC load line analysis, we can still take the same equation. VCE is VCC minus ICRC. The graph is going to look exactly the same. Everything we discussed in the fixed bias is applicable here also. Let us now solve a problem. We have a transistor and we have biased it using the voltage division method. VCC is 2.5 volt, IS is 10 raised to minus 17 ampere, beta is 100, RC is 5 kilo ohm, R1 is 17 kilo ohm and R2 is 8 kilo ohm. We have to check if Q1 is in forward active region. What is Q1? It is the name of the transistor. Since we are using the voltage division method, the first thing we have to make sure is that the base current is negligible. Let us do that. But first, we will find out how much is Vx. Vx is R2 divided by R1 plus R2 multiplied by VCC. Giving all the values, we get 800 millivolt. Using Vx, let us calculate the collector current. Collector current is Is e raised to VBE by VT, but VBE will be Vx this time. Giving the values, we get 231 microampere. We know base current is collector current divided by beta, and the value of beta is also given in the question. So we can write IB is IC by beta. Giving the values, we get 2.31 microampere. How do we decide if it is negligible or not? What should we compare IB with? See, we have a current I flowing through R1. We want to make sure whatever part of it goes into the base is very less. So we have to compare IB with I, the current that is flowing through R1 and R2. That current will be VCC divided by R1 plus R2. We get this is approximately 100 microampere. IB is around 2.31 microampere. 100 microampere is actually around 43 times 2.31 microampere. That is, the current I is 43 times the base current, which means obviously base current is negligible. Now, to check whether the transistor is in forward active region, we have to make sure if VCE is greater than VBE. We have to find out VCE. We know VCE here is VCC minus ICRC. Let us give the values and we get VCE is 1.345 volt. This is obviously greater than VBE, which means Q1 is operating in the active region. Let us now see how we can analyze the voltage divider bias in a different way. For that, I have modified the circuit slightly like this. Instead of showing how VCC is connected to both RC and R1 in one go, I have given them separately. Still, RC is getting VCC, R1 is also getting VCC, so this is not going to affect the circuit in any way. So at the input, we have a voltage divider circuit. Let us take it out. I am going to draw the Thevenin equivalent of this circuit. Output is taken over here. We are giving VCC over here. VCC is basically a cell that is connected like this that goes to the ground. So I can draw the same circuit like this. VCC is modeled as a cell. Its positive terminal goes to R1 just like over here. R1 goes to R2 and then it goes to ground. Here also same thing happens. Between R1 and R2 we are taking the output. Here also between R1 and R2 the output is taken. To draw the Thevenin equivalent of the circuit, we have to find out the Thevenin voltage and the Thevenin resistance. Thevenin voltage is whatever is the voltage you get over here. That's pretty easy to find. You can apply KVL or voltage division or whatever you want. Voltage that you get over here is the voltage that is dropped across R2. Supply is VCC, so it is going to be VCC divided between R1 and R2 and whatever R2 gets. Thevenin voltage is R2 by R1 plus R2 multiplied by VCC. We need to find out the Thevenin resistance also. Obviously, in this circuit, we only have independent sources. That makes our job easier. The only thing we have to do is switch off all the sources. If we do that, circuit will look like this. I have shorted VCC because VCC is a voltage source. Now I have to find out what is the equivalent resistance I get here. Basically, R1 is connected in parallel to R2. So the equivalent resistance is going to be R1 parallel to R2. That will be the Thevenin resistance. Now this means whatever we have over here can be modeled as a voltage source of value R2 by R1 plus R2 VCC that is in series with a resistor whose value is R1 parallel to R2, like this. Now, instead of connecting this to the base of the transistor, we can connect this. The circuit will work exactly the same. Let us do that. This is what we get. Let us apply KVL in this loop. We have the base and emitter, so this is the base emitter loop. I'll start from this point and go clockwise. I can see VTH from negative to positive. As I go on, I can see there is a resistor RTH, so obviously some voltage drop is going to be there. The current flowing through RTH is our base current IB. It is flowing in this direction. So the resistor should have positive potential here, negative potential here, which means the potential drop across it is opposite to VTH. So I will write minus IB RTH. As I go on further, I can see the base emitter junction. Voltage across it is VBE. Again, positive is here, negative is here, so minus VBE. Base is here, emitter is connected to the ground. So VBE is whatever is the potential I get here with respect to this point, but I have called this point X. So VBE here is equal to Vx, which means instead of writing VBE, we can write Vx. According to KVL, this should be equal to 0. This gives us Vx is VTH minus IB RTH. Using this, we can write the expression for the collector current. The collector current is IS e raised to VBE by VT or IS e raised to Vx by VT, and this makes our bias relatively insensitive to the value of beta. All good. Let us try something else. we got IC is Is e raised to Vx by Vt. Obviously, Vx does not depend on beta, it depends on the supply VCC and the resistors R1 and R2. We know resistance is dependent on temperature. Let us assume R2 becomes just 1% higher because of temperature. That means Vx will also become 1% higher because Vx is basically the voltage that is across R2. And according to Ohm's law, V is equal to IR. V is proportional to R. So if R changes 1%, V also changes 1%. If Vx becomes 1% higher, the new Vx is going to be original Vx plus 1% of Vx. That is 1.01 Vx. Then the new collector current will be Is multiplied by e raised to 1.01 Vx by Vt. 1.01 Vx can be written as Vx plus 0.01 Vx. Is e raised to Vx by Vt multiplied by e raised to 0.01 Vx by Vt. This thing was split into two like this. Now, Vx is equal to VBE. We can assume VBE is 0.7 volt. Vt is the thermal voltage, it is 26 millivolt. If we give the values, we can find out what is e raised to 0.01 Vx by Vt. It comes out to be 1.31. Also, what we have over here is Is e raised to Vx by Vt, which is our original collector current. So the new collector current is 1.31 times the original collector current. That means the collector current increased by 31%. R2 changed only 1%. That made our collector current change 31%. So it's true that collector current became relatively independent of beta, but now we have a new problem. It depends on the resistance. This dependence is again going to destabilize our Q point. So we have to do something to stabilize it. Let us try this. There is one resistor at the emitter and I have called it RE. This method is called emitter degeneration. Let us see how it works. I have marked this point as P. So potential here can be taken as Vp. This point is X. Potential here can be taken as Vx. X is at the base. So we can write potential at the base Vb is equal to Vx. The same way P is at the emitter. So potential at the emitter Ve is actually just Vp. Now if I want Vbe or the base emitter voltage, which is basically Vb minus Ve, I can write it as Vx minus Vp. Without emitter degeneration, emitter was directly connected to the ground. So Vp was 0. In that case, we got Vbe is Vx minus 0 or equal to Vx. With emitter degeneration, it becomes Vx minus Vp. Using this, we can update the expression for our collector current like this. It will be Is e raised to Vx minus Vp by Vt. Vbe is Vx minus Vp. Now forget about the math. Let me give you an idea on how emitter degeneration or basically simply adding a resistor at the emitter is going to help us stabilize our Q point. Without emitter degeneration, our problem was that when Vx increases a little bit, Ic increases a lot. Assume that we have a collector current Ic and it increases when Vx increases. Now, when Ic increases, obviously IE is going to increase. IE is the current that flows through RE. The potential across RE will be IERE. If IE increases, IERE also increases. But what is IERE? It is VP. So we can write VP increases. Basically, when Vx increases, Vp increases. In the equation of collector current, we have Vx minus Vp. If Vp increases when Vx increases, then Vx minus Vp is going to be the same. If Vp decreases when Vx decreases, then also Vx minus Vp is going to be the same. So Vx minus Vp remains relatively constant, and that makes IC relatively constant. So simply by adding a resistor at the emitter, we can stabilize our Q point. Now that the idea is clear, let us do the analysis mathematically. The first thing I did is this. I took the voltage divider circuit and replaced it with its Thevenin equivalent circuit. We already did this, so I'm sure I don't have to explain it again. Here the Thevenin voltage will be R2 by R1 plus R2 VCC. Thevenin resistance will be R1 parallel to R2. Let's take this loop. It is the one with the base and emitter, so we call it the base emitter loop. Let's apply KVL in the base emitter loop. I'll start from this point and go clockwise. I can see VTH is from negative to positive. I will write VTH. As I go, there is RTH. Current in RTH is IB and it is flowing in this direction. So the potential have to be positive here and negative here. It is in the opposite direction. So I will write minus IB RTH. As I go on further, I can see the base emitter junction. Potential across it is VBE. Positive is at the base, negative is at the emitter, so minus VBE. Further as I go on, I can see RE. Current flowing through RE is the emitter current IE. IE flows in this direction. We know current only flows from positive potential to the negative potential. So RE must have positive potential here and negative potential here, which is again opposite to VTH. So I will write minus IERE. According to KVL, this has to be equal to 0. Now we have IE over here. We know IE is the sum of the collector current and base current. And collector current can be written as beta IB. So IE is beta IB plus IB or beta plus 1 IB. Let's replace IE by beta plus 1 IB. Rearranging this equation, we can write an expression for IB. IB will become VTH minus VBE divided by RTH plus beta plus 1 RE. We know beta is supposed to be a large number. So beta plus 1 can be considered approximately equal to beta. Then IB can be approximated to VTH minus VBE divided by RTH plus beta RE. Let us now take the collector emitter loop. That is this one. We reach the collector, we go to the emitter. This is ground, but then VCE is also basically a cell that is connected to the ground. So we have a loop here. Let us apply KVL in the collector emitter loop. I'll start from this point and go anti-clockwise. First I have VCC. As I go on, I can see RC, so there is going to be some potential drop across it. Current flowing through it is IC in this direction. So RC must have positive potential here and negative potential here, which is opposite to VCC. VCC was supposed to be negative to positive like this. So I will write minus ICRC. Further as I go on, I am at the collector and I go to the emitter. So what I have here is the collector emitter voltage or VCE, which is again positive to negative. So I will write minus VCE. As I go on further, I have RE again. Current flowing through RE is IE in this direction. So obviously we have positive potential here, negative potential here. I will write minus IE RE. According to KVL, this should be equal to 0. One approximation we can make is this. Since IB is really small, IE will be approximately equal to IC. So we can replace IE in the equation by IC. We get VCC minus ICRC minus VCE minus ICRE is equal to 0. Here we can write an expression for VCE. We get VCE is VCC minus IC multiplied by RC plus RE. Without emitter degeneration, the equation was VCC minus ICRC. Now we have VCC minus IC multiplied by RC plus RE. Let's do the DC load line analysis with this equation. We have to plot the graph between IC and VCE. This is also the equation of a straight line. If IC is 0, you can see VCE will be equal to VCC. If VCE is 0, you can see IC will be VCC divided by RC plus RE. If we draw the graph, this is how it will look like. When IC is 0, VCE will be equal to VCC. So this point is corresponding to VCC. When VCE becomes 0, IC will be VCC by RC plus RE. So at this point, we get VCC by RC plus RE. Let's overlap the IV characteristics of the transistor in this graph. I'll also choose a Q point just for fun. I'm giving VBE2, that means I'm getting this much collector current. But according to the DC load line, this much collector current requires this much VCE. So my Q point will be over here. Let us now solve a problem. We have to calculate VCE and IC. R1 is 39 kilo ohm, R2 is 3.9 kilo ohm, RC is 10 kilo ohm, RE is 1.5 kilo ohm, and VCC is 22 volt. Before we solve this, let me explain something else to you. You can see R1 is 39 kilo ohm and R2 is 3.9 kilo ohm. R1 is 10 times R2. Is it intentional or just a coincidence? Well, R1 being exactly 10 times of R2 is not important, but R1 being significantly larger than R2 is important. This is the reason why. We are applying VCC over here. If R1 is really large, most of VCC will be dropped across R1. Only the rest of the potential will be dropped over here. That means the potential at base will be lesser if R1 is significantly higher than R2. If VB is lesser, IB will also be lesser. You already know why base current being negligible is important for voltage divider bias. So we need R1 to be significantly higher than R2. As a thumb rule, while designing a circuit, we take R1 to be 10 times of R2. Now to solve the problem, I will redraw the circuit, but this time instead of the voltage divider bias, I will take its Thevenin equivalent. The circuit will look like this. Let's find the value of RTH first. It is R1 parallel to R2, or giving the values, we get 39 multiplied by 3.9 divided by 39 plus 3.9, and this becomes 3.55 kilo ohm. We also have to find out the Thevenin voltage. It is R2 by R1 plus R2 multiplied by VCC. Giving the values, we get 2 volt. Now let's find the base current. IB is VTH minus VBE divided by RTH plus beta plus 1 RE. We have all the values except beta. Let us take beta to be 100. That will give us base current is 8.38 microampere. We need to find the collector current, but it is beta multiplied by the base current. So IC is 0.84 milliampere. We also need VCE. VCE is VCC minus IC multiplied by RC plus RE. We have all the values. If we give them, we get VCE is 12.34 volt. Let us now try another way of biasing the transistor. Here, instead of directly taking VCC through a resistor to the base, I am taking voltage from the collector through a resistor like this. This method is called self-bias. Let us understand how it works. I'm calling this point X and I'm calling this point Y. X is actually the base and Y is actually the collector. Here you can see that whatever is the potential we have at Y, some of it will be dropped across RB and the rest will be dropped at X. So I can say Vx is Vy minus potential across RB. The current that flows through RB, you can see that it is the base current. So potential across RB is IBRB. That means Vx is Vy minus IBRB. X is at base and Y is at collector. So Vx is Vb, Vy is Vc. So we can write Vb is Vc minus IBRB. Base voltage is collector voltage minus something. That means base voltage is always going to be lower than the collector voltage. Or we can write, since Vc is greater than Vb, Vc with respect to the emitter is going to be greater than Vb with respect to the emitter. And that means the transistor is always going to be in the active mode. No matter what happens, the transistor is not going to saturation. Now let's do the math of it. Before that, you can see I have marked IC as the collector current. It is the current that is going into the collector. Now, over here we have a junction. Current that flows in this direction is our base current IB. So, basically, some current flows through RC. Out of it, IB flows in this direction, IC flows in this direction. Using Kirchhoff's current law, this current has to be the sum of IB and IC. We are going to assume that IB is very much smaller than IC. That means whatever is the current that is flowing through RC, a very small amount goes in this direction. Almost all of it goes through this direction. So we can approximately say the current that is flowing in RC is equal to IC. This is the assumption we are making. We assume IB is very much smaller than IC so that the current through RC is approximately equal to IC itself. Now we give VCC here. Out of that, some potential drops across RC, the rest will be given at Vy. So I can say Vy is VCC minus whatever is dropped across RC. Now we have assumed that the current flowing through RC is IC itself. So the potential across it is ICRC, which means Vy is basically VCC minus ICRC. But over here we have Vx is Vy minus IBRB. From there we can write Vy is IBRB plus VBE. Now IB can be written as IC divided by beta. So Vy can also be written as RB IC by beta plus VBE. Now this is Vy, this is also Vy. Let us equate them. VCC minus ICRC is equal to RB IC by beta plus VBE. Rearranging this equation, let us find an expression for IC. We get IC is VCC minus VBE divided by RC plus RB by beta. But there is a problem. We have beta in the equation for IC. We have already discussed why IC should not be dependent on beta. So we have to do something. To minimize the sensitivity of IC to beta, we take RC to be very much larger than RB by beta. Then over here in this equation, in the denominator, RC plus RB by beta can be approximated to just RC, because when compared with RC, RB by beta will be really small. Then the equation of IC becomes VCC minus VBE by RC. Let us now solve a problem. We have a transistor that is under self-bias. You can see there is a resistor at the emitter also. So this is self-bias with emitter degeneration. Emitter degeneration is only going to stabilize our Q point, so let it be there. We have to calculate VCE and IC. VCC is 10 volt, RE is 1.2 kilo ohm, RB is 250 kilo ohm, RC is 4.7 kilo ohm, beta is 90. Let us start by applying KVL in the base emitter loop. I mean this one. We reach the emitter, we go to the base, we go through RB and then RC to VCC, which is just a cell that goes back to the ground. I'll start from VCC. Current through RC is IC, so a potential drop of ICRC will be there. I have to write minus ICRC. As I go on, I have RB here. Current through it is IB. So IBRB will be dropped across RB. I have to write minus IBRB. As I go on further, I reach the base emitter junction. So I have to write minus VBE. Further as I go on, I can see RE. Current across it will be IE. So the potential drop will be IERE. I have to write minus IERE. According to KVL, this will be 0. Now, we can assume IE is approximately equal to IC and write the equation like this. Instead of IE, I have written IC. Again, IC is beta IB. So I am going to replace both ICs with beta IB. The equation becomes like this. We get VCC minus beta IBRC minus IBRB minus VBE minus beta IBRE is equal to 0. Let us rearrange this equation so that we can find an expression for IB. I got IB multiplied by beta RC plus RB plus beta RE is equal to VCC minus VBE. From here, we can easily write IB is VCC minus VBE divided by RB plus beta times RC plus RE. We have all the values. Let us substitute them and find out the value of IB. IB comes out to be 11.91 microampere. Since we have IB, we can find out IC. IC is beta times IB. Beta here is 90. So we get IC is 1.07 milliampere. We also have to find out VCE. For that, we can apply KVL in this loop. It has the collector and emitter, so it is the collector-emitter loop. I'll start from VCC. ICRC will be dropped across RC over here, so I will write minus ICRC. As I go on, I have the collector here and emitter here, so this much potential is VCE. I will write minus VCE. Further as I go on, I have RE here, current across it is IE, so the potential drop is IERE. I can write minus IERE. According to KVL, this should be equal to 0. Now IE is approximately equal to IC. So here instead of IE, we can write IC. We have to find out VCE. We can write an expression for VCE. It is VCC minus IC multiplied by RC plus RE. You can see this is exactly the same when we had the emitter degeneration in the voltage divider bias. We have all the values. Let us substitute them. We get VCE is 3.69 volt. Let us summarize what we learned. First, we tried to bias it directly from VCC, which did not work. Then we had fixed bias where we took VCC through a resistor RB, but then IC was too sensitive to beta. Then we figured we could use a voltage divider that significantly made IC independent to beta, but here it was sensitive to resistor errors. So to stabilize the Q point, we added a resistor at the emitter and we called this the emitter degeneration. Emitter degeneration made sure that IC will relatively become constant, and once the transistor is in active mode, it will stay in active mode. After that, we learned self-bias. Here also the transistor will stay in active mode forever. And in the last problem, we saw that we can even add emitter degeneration in the self-bias and make the bias more stable. So that's all about it for today. See you in the next video. And don't forget to subscribe.